You know, our planet is wrapped in these massive invisible rivers. And no, I'm not talking about rivers on land. These are powerful currents deep in the ocean. And they pretty much run the show, dictating our weather, shaping our climate models, even guiding global shipping. And figuring out how to actually map them, well, that's one of the biggest challenges in understanding our world today. But that leads to the billion-dollar question, right? How on earth do you map something so huge and powerful when you can't even see it? Today, we're going to dive deep into that incredible challenge, charting the invisible superhighways of our oceans. So, for decades, scientists have had two main ways of tackling this. But here's the thing. Each one gives a totally different picture of the sea. It's kind of like trying to understand a giant city by looking at a single street sign and then comparing that to a blurry photo taken from space. You're getting two very different stories. Okay, so let's break down the classic tools in the oceanography toolkit. You've basically got two options, things you can physically toss into the water, and then you've got your eyes in the sky. And that brings us to the two main players, drifters versus satellites. Think of drifters as these super high-tech messages in a bottle. They just float along and give us this incredibly precise boots on the ground, or fins in the water, view of one tiny path. Then you've got satellites. They give us the big picture, right? A huge global snapshot. But they miss all the juicy, fine-grained details. And this right here, this shows you the problem perfectly. Take a look at the left. That's the data from the drifters. See all that amazing, intricate, almost chaotic detail? That is what's really happening down there. That's the complex flow of the water. Now, look to the right. That's what the traditional satellites see. It's a lot smoother, a lot blurrier. It gets the main highways, for sure, but it completely misses all the local streets and back alleys. So the big challenge is, how do you get these two completely different datasets to talk to each other? How do you make the super detailed street view and the blurry satellite photo tell the same story? Well, the key is knowing that there are basically two types of currents. You have the big, stable ones called geostrophic currents. Just think of those as the ocean's interstate highways. Then there's everything else. All the little local eddies and wind-driven swirls. That's all called ageostrophic. Now, here's the critical part. Drifters measure everything, the highways and the side streets. But the old-school satellites, they pretty much only see the highways. So to fix this mismatch, scientists get clever. They use these sophisticated mathematical tools. One is called a Hanning filter. What it does is pretty cool. It basically acts like a noise-canceling headphone for the data. It strips out all that ageostrophic noise, the local disturbances, from what the drifters are picking up. And what you're left with is the pure, clean signal of that main highway current. And get this, it worked. By applying this filter, the drifter data suddenly matched the satellite view of the north-south currents 16% better. Now, 16% might not sound like a lot, but in oceanography, that is a huge leap forward. It was proof that they were finally getting these two very different views of the ocean to speak the same language. But what if you didn't need the filter at all? What if a satellite could actually see with the same kind of detail as a drifter on the ground? Well, hold on, because a revolutionary new satellite named SWOT is trying to do exactly that. And believe me, it is a total game changer. Okay, so SWOT, which stands for Surface Water and Ocean Topography, launched back in 2022. It was designed from the ground up to give us this totally unprecedented high-definition view of the ocean's surface. Seriously, it's like we've been watching on an old fuzzy tube TV and someone just handed us an 8K remote. And wow, the difference is just night and day. On the right, you've got that familiar view from the older satellites, smooth, a little blurry. But then look at the SWOT data on the left. I mean, just look at it. You can suddenly see all these tiny, swirling eddies, these beautiful, fine filaments. These are structures we could barely even guess existed before. It is literally like seeing the ocean in high def for the very first time. But this brings up a really crucial, almost philosophical question for the scientists. I mean, anytime you get a shiny new instrument that shows you things you've never, ever seen before, you have to step back and ask, is all this incredible, beautiful new detail real? Or is it just really convincing noise? So to find out, a recent study set up the ultimate test. It was a showdown. SWOG's brand new high-def data versus the ground truth. And what's the ground truth? Well, it's our trusty old ocean drifters, the ones that are actually out there, floating in the real currents. And the results? Well, they were fascinating, and a perfect example of how science almost never gives you a simple yes or no answer. So this table shows the correlation. That's basically just a score for how well the satellite data matched the real-world drifters. A perfect score would be a 1. Now, look at the east-west currents. The old satellites, they scored a 0.20. Not great. But SWOT? It jumped all the way to 0.60. That's a massive improvement. But then you look at the north-south currents, and things get weird. Okay, so let's be clear. That huge jump to a 0.60 correlation for the east-west currents, that was a home run, a resounding success. It proved, without a doubt, that SWOT was seeing that part of the ocean's flow with incredible, game-changing accuracy. But here is the twist in the story. For the currents running north to south, it performed no better than the old blurry satellites. So what on earth is going on here? Why the huge difference? Well, the answer, it turns out, is in the satellite's design, how it was literally built. SWOT looks at the ocean in these two long, narrow strips, or swaths. And that shape is fantastic for measuring changes along its long side, but it's much, much harder to accurately calculate the currents across its narrow side. So the satellite's physical design makes it inherently better at seeing east-west currents than north-south ones. No, this isn't a failure, not at all. It's a discovery, and it tells us something really profound about how science actually works. You see, every new tool we build, every satellite we launch, it gives us a clearer, more amazing picture of our planet. But at the same time, it almost always reveals new complexities, new challenges, new mysteries we didn't even know existed. And that's not a setback, that is progress. One of the researchers on this project, Julio DONFACK, summed it up perfectly. He said that SWOT gives us much better information for that zonal, or east-west part. But the meridional, the north-south part, is less precise. And that right there, that constant cycle of innovating, testing, and finding new challenges to overcome, that is exactly how science moves forward. So the big takeaway here is that we are really just beginning to see the true intricate dance of our oceans. SWOT has pulled back the curtain, showing us details we never even knew were there. And that leaves us with one final and really exciting question. What else is out there just waiting for the next generation of satellites to discover?